Geometric random variables are very important. Random variables of the geometric type. X is distributed, geometric P, if it models the number of independent Bernoulli P trials until the first success. This is what you need to know about geometrics right here. This is, whenever we cover any of these so-called famous random variables, the most important thing is that you understand their meaning. What is it about them that's important? What is it that we use them to model? Okay, what are we trying to model with them? Because I'll show you, just like we did with binomials. If you know that, then the form of the probability mass function, the mean, the variance, all this other stuff can be derived. Okay, so geometrics model the time until the first success when you do something over and over independently, and each time you have a success with probability P. For example, the time machine's engine starts independently each time with probability 1/10. Okay, if Marty goes to start the time machine, what's the probability that it starts for the first time on the 4th try? What's the chance that he turns the ignition and nothing happens, turns the ignition, nothing happens, turns the ignition, nothing happens, and then finally on the 4th time he has success? Well, by independence, right, since these are independent trials, I can just multiply the 4 probabilities. It's the chance that he doesn't start times the chance that he doesn't start times the chance that he doesn't start, and then finally times the chance that he does start, right? Okay. So this is actually by independence and the rule for complements, right? The chance that it doesn't start is going to be 0.9 if the chance that it does start is 0.1. Okay. What's the chance that it starts for the first time on the 10th try? Well, it's 0.9 to the 9th times 0.1, because he's going to fail 9 times in a row and then finally get it going on the first for the first time on the 10th try. Okay, so that comes out to be about that. Okay, so in general, what's the probability mass function for a geometric P? Well, this sort of tells us, I mean, if you think in more general terms, then this is how it should be, right? The chance that our geometric takes on the value of k, it's 1 minus p raised to the k minus 1 times p, where k has to be an element of the strictly positive integers. Okay, it could be 4, it could be 1,000, it could be 1,000,000. Okay, so this is not a finite set. This is a very different kind of thing from a Bernoulli random variable or a binomial even. Okay, binomials take on values from 0 up to the number of trials. In a binomial, you fix the number of trials, and then you execute that many trials. Here, in the geometric case, you're looking at doing trials over and over and over again until you see the first success. All right, so let's do another example here. Back to this time machine business, what's the chance it takes at least 4 attempts before you see a start? At least 4 attempts. So if x is the number of attempts until the first start, okay, then, by the way, I guess then x is distributed geometric with parameter a tenth, right? X is distributed geometric with parameter 1/10. So the chance that x is at least 4, that's what we want. I could write it like this, right? It's because if the chance that x equals 4, that's going to be 0.9 to the 3rd times 0.1, right? Okay, so I'd want my exponent here to actually start with 3. If k equals 3, then this stuff is the chance that x equals 4. Then I have to add to it the chance that x equals 5, plus the chance that x equals 6, plus the chance that x equals 7, so forth and so on. Right? This is by axiom 3, because see, this event, x is greater than or equal to 4, is really the union of a bunch of disjoint events where x equals 4 or 5 or 6 and so forth. So I'm just summing up those probabilities. Okay, so here's what I'm going to do. I'm going to pull this 1/10 out of the sum, because I think I know how to deal with that sum now. I know something about about these. This almost looks like the infinite sum where k goes from 0 to infinity of all this stuff, doesn't it? Yeah. In fact, I could just change it to that, and that would be okay, because I know how to deal with that, right? If this instead, if it were like that. Now, to maintain equality between these two expressions, I have to compensate, right? I need to subtract off 0.9 to the 0 minus 0.9 to the 1 minus 0.9 to the 2th, right? See that? Now these things are the same. Now these things are the same. Now, I know how to deal with this sum, don't I? I think so. Do I know that? Yeah. It's 1 over 1 minus 0.9. Okay. And then minus 0.9 to the 0 is 1, minus 0.9, minus 0.9 squared, I guess. And all of this is 10, so it's 0.1 times 10 minus 1 minus 0.9 minus 0.9 squared. All this should come out to be 0.729. Okay. Yeah, very good. Very good. Now that's pretty complicated. It turns out there's a much easier way. There's a much easier way. I'll do it like this. I'll do it over here. You say big fat, or the chance that x is at least 4. Can I say that that's 1 minus the chance that x is less or equal to 3? Yeah. Actually, yeah. So I could do it that way and say it's 1 minus the probability that x that x equals 0 minus the chance that x equals 1 minus the chance that x equals 2 minus the chance that x equals 3, right? So, in fact, made a little silly something here. Of course, x cannot be 0. So what is this going to be? It's going to be 1 minus, what's the chance that it happens on the first time? 0.1 minus, what's the chance that it happens on the second time? 0.9 times 0.1. What's the chance that it happens the first time on the third time? It's 0.9 squared times 0.1. And in fact, if you do that with your calculator, you'll see that you get 1 minus 0.1 minus 0.1 times 0.9 minus 0.9 squared times 0.1. 0.729. Yep. There's an even easier way to do this problem. Oh, you're going to love this. Go back over here. Look at this. You see that? The probability that it doesn't start 3 times, then starts on the 4th time. This gives me a big hint, I think. Guess what? It will start for the first time on the 4th time or later, if and only if it doesn't start the first 3 times. So guess what? So the chance that x is at least 4 is the chance that it doesn't start. Doesn't start the first 3 times. Okay, those events are equivalent, and so that's just 0.9 cubed, which is 0.729. How about that? Great. Do your homework.